All right. So uh, we already talked about the duration of the illumination pulse. We talked about that the illumination duration of the pulse should be short enough to freeze the motion of the particles during the pulse exposure in order to avoid blurring of the particle images, that is, no streaks. We also said that the time delay is important because otherwise, if the time delay is too much, then the particles may either go out of the measurement window. If there is out of plane component, it might go out of the plane. And but if it is too short, then the particles may not actually move. So all these things are important, and the rep rate of the lasers is also important. So other points are that the objects within the flow. So for example, the glare may be present. In the vicinity of the objects within the flow, such as wind tunnel models, due to the reflections of the light which is hitting the surface of the model. So therefore, these acts as glare points. This is due to reflection. And this experimental setup needs to be optimized by changing the angle of the incident light or by covering the model surface with paints. Sometimes special fluorescent paint are applied and blocking this fluorescent light with narrow bandwidth interference filter. We already know what those filters are. So these filters are placed tuned to the frequency of the illuminating light. So therefore you capture only, the light which has got the same frequency. When you coat it with a fluorescent paint, the emission signature will be at a different frequency or a different wavelength. Therefore, you are neglecting it. But if there is a glare point present, it will have the same frequency as the scattering. As a result of that, it can create problem. So therefore, you coat it with fluorescence so that the emission, whichever light falls on that particular object which is painted with a fluorescence paint, that will now have a different emission wavelength. As a result of that, if you use a narrow bandpass filter, you should be able to collect only the laser light, which now should be coming from the tracer particles. Now, triggering, many light sources used for PIV, such as standard double pulse Nd:YAG lasers, operate with a given repetition rate. Now, the triggering such lasers, including their flash lamps and Pocal cells and the recording cameras, these are usually done by delay generators or customized timing units, which is programmable timing units, as I call it. So this can be kind of tuned to the nanosecond, so that everything is kind of in sync, because you want the laser light to come and the camera should also open at the same time. So everything needs to be synchronized like that. So the number of components of the velocity vector, if it's a planar illumination, you can only get 2 in-plane components. You cannot get the out-of-plane components. For that, you need a second camera, which gives you the stereo vision, like your eye. So it should give you that the third component is possible. All right. So the temporal resolutions, so the standard PIV systems allows you to record with high spatial resolutions, but at relative low repetition rates, right? However, if you now look at the high-speed lasers and high-speed cameras, which allows time-resolved measurements in most liquid and aerodynamic flows, the time-resolved PIV should be used. But however, if it cannot resolve a flow field, which is very high speed, we can say high-speed PIV. Time resolved means you are resolving all aspects of the flow field, whereas high-speed PIV means you are probably resolving some aspects which are within the measurement temporal window, but you are not resolving everything. It's like the turbulence, right? So you can resolve some and you are not resolving the others. But fully resolved means you are resolving all scales, right? So then comes the spatial resolution, which is basically the size of the interrogation areas during evaluation must be small enough for the velocity gradients interrogated not to have significant influence on the results. So it cannot be very large, so that within the measurement window itself, the velocity gradient is so sharp that within the measurement window itself, there is a variation in velocity. Remember, within that interrogation windows, we are not assuming that there is a spatial gradient of velocity that is present. So we have to make, in those cases, the window sizes really small, the interrogation window sizes really small for you to be able to resolve the flow field. So in the areas of strong velocity gradients, like you would do in your CFD, you reduce the cell size. Here also, you have to do the same thing. All right. Okay. Now, you also have this, temporal versus spatial resolution. So this is usually a compromise between a spatial and the temporal resolution, depending on the objectives of your measurement, right? So as evaluation methods, when you go to evaluation methods, we already said that the PIV technique works on ensembles of images of the tracer particles and statistical correlations of the correlation methods for evaluation. Whereas in the case of PTV, which is particle tracking velocimetry, it works with single identifiable images of the tracer particles and tracking methods. The PIV techniques delivers results on a regular grid, whereas PTV delivers results on an irregular grid. Okay. You also need to be careful about the repeatability of the evaluation. So in PIV, the full information about the flow field is stored at the time of recording, and then you can post-process it in whatever ways you want. So these are some of the examples. This is a highly three-dimensional flow field, and these are the flow field. These are very complex flow fields which the PIV is able to resolve. So this is the power of particle image velocimetry. Look at the type of velocity information and vorticity information that you can get. Now that we have done this, let us take a look at the tracer particles. We already said that is the backbone of PIV measurement, right? So the measurement technique is indirect. We already said that the velocity of the tracer particles instead of the velocity of the fluid. Therefore, the interaction of the particles and the surrounding fluid has to be examined, because we are talking about that the particles actually follow the flow field. So therefore, the optical properties of the seeding particles also play an equally important role for the selection of suitable tracers. So let's look at the fluid mechanical properties first. Okay. The primary source of error is the influence of gravitational force on the velocity of the tracer particles, because these are particles. They have some weight. As a result of that, there is a gravitational pull, and the particles may actually sediment. So if the densities of the fluid and the tracer particles do not match, so say the density of the fluid is rho and the tracer particle density is rho b, obviously they do not match in most of the cases, or rho p rather. Even though it can be neglected in many practical situations, we would now try to say that what happens when you have a gravitationally induced velocity which comes from the Stokes drag law. Okay, to introduce the particle's behavior under acceleration. Okay, so let's assume that there is spherical particles in a viscous fluid at a very low Reynolds number. So G is the acceleration due to gravity, mu is the dynamic viscosity of the fluid, dp is the diameter of the particle, and the equation implies that there is sedimentation tendency, or so ug is the gravitationally induced velocity. So this sedimentation can be avoided if the density of the fluid and the particles is identical. So if this particular term goes to 0, which is rho p minus rho, then this ug, which is the gravitationally induced velocity, would be also equal to 0, correct? In another way, this types of particles which are identical in density to the fluid. This is called neutrally buoyant particles. And this is easily achieved in the case of liquid flows. You can have particles which has got the same type of density as the fluid medium. Okay. In the gas flows, however, this density difference is typically much higher than the fluid, because it is air and the particle is some kind of a liquid or another particle. So air is 1, the other particle may have a density closer to 1000. So this becomes like 1000. So therefore, the particle diameter, you have to make it very small to minimize the settling velocity, because you see the other term here is dp square. So if you reduce the diameter by half, the settling velocity goes down by 1/4. So it's a square dependence, right? So if you kind of decrease the particle diameter, you can achieve the same effect as reducing the density. So there are two players basically here. the difference in density, and the diameter of the particle. Now, this is the interesting part, that in this case, if you are an experimentalist, what are you going to do? In the case of liquid, you can have the liberty of choosing larger particles. But in the case, because you have a density difference which is practically equal to 0. However, if you are in the gas phase, you have to make this very small to account for the 1000 increase, because air is normally 1, particle density is normally of the order of 1000, even if you use a liquid or a solid particle even, right? So you need to reduce this by quite a bit to achieve the same, minimize the settling velocity, so to say, right? So, but this, we can also derive an estimate for the velocity lag of a particle when it is continuously accelerating in a fluid. Okay. So say UP and U denote the particle and the surrounding fluid velocity. Rho P is the particle density. In case of sudden deceleration, the step response, UP, typically follows an exponential law. Okay. And if the density of the particle is much greater than the fluid density, then this is the expression that you actually get. Okay. So in other words, what you can see that US is the deficit, is the velocity deficit. So U is the actual velocity and UP is the particle velocity, right? So this suddenly gets accelerated by A. Okay. That is what you see. There is a sudden acceleration now, okay, on the particle. Now the surrounding fluid velocity, and rho p is the particle density. In this case, in the case of sudden deceleration, it typically follows an exponential law, where the response time is given by this, which is tau p equal to dp squared into rho p divided by 18 mu. So if the fluid acceleration is not constant, or Stokes drag does not apply, example for larger particles or at very high flow velocities, the solution is no longer an exponential decay of the particle velocity. All right, because this is in the case of a deceleration, remember. All right. Nevertheless, this tau p remains a convenient measure for the tendency of the particles to attain the velocity equilibrium with the fluid. This is the time scale at which the particle attains the equilibrium, the velocity equilibrium with the fluid. Okay, this is the time scale. This is the time scale that comes because there is an exponential. Okay, so knowing that the response time of a particle tracer is not sufficient, but however, if we just know that response time, so this is the response time of the particle tracer to an acceleration or a deceleration, right? So not valid for very large particles or very high flow velocities, right? Okay, so but if you know the response time of the particle tracer, it is not sufficient to determine if it will follow the flow with enough fidelity. Okay, for that you need what is called a Stokes number. So Stokes number is nothing but the ratio of the two time scales. One is the particle response time, the other one is the characteristic time of the flow. So if the particle response time is much smaller than the flow time, that is the flow rollover time, say for example, this particular characteristic time may be the shedding scale of a vortex, if that is what you are trying to measure. And if the particle response time is much smaller than the vortex shedding time, then you should imagine that the Stokes number should be a number which is much less than 1. And if it is less than 1, it should be able to follow the flow with enough fidelity. So the rule of thumb is that a value of Stokes number which is less than 10 to the power of minus 1 yields an acceptable flow tracing accuracy. Remember that. Okay, so it is not enough just to know the response time, but it is also important to determine the Stokes number to see whether this response time is lower than the flow characteristic time. So you can imagine if the vortex is being shed at a very high frequency, for you to determine the vortex, that means for the particles to trace the vortex, that means that is what you are going to measure. So if you are supposed to measure that tracer wiggling in the vortex, then the tracer time scale has to be much lower than the vertical time scale. All right, and that sometimes is pretty onerous. That means your tau p, if you look at it, it should have a time, it should have a diameter which is very, very small. Because smaller the diameter, actually, if the diameter falls by half, the response time scale falls by 1/4. Okay, and you can also reduce the density, which is the basic paradigm anyways. You need to reduce the density. You also need to reduce the particle diameter if you are to track this high speed flows or flows which has got very low flow time scale. Right. So this is, for example, the Umax, and this is the relaxation time. For example, a 1 micron droplet relaxes from Umax to Umean in a very short time interval. This is in microseconds. Whereas if you see a 5 micron, it takes about, say, 200 microseconds to reach to about, say, 1.1 of the mean. And then it takes a very long time, very, very long time, 600, 800 microseconds for a 10 micron droplet to attain the same thing. This is the theoretical time response of oil droplets with different diameters in air after an instantaneous flow deceleration. Okay, so there is a deceleration of the flow. It is a step function. Say that it is a step function, and this is the time that it takes for the particles to respond. So this is quickest, this is the longest. So in air flows, particles with same overall density as the air can be generated by using liquid bubbles filled up by a gas lighter than air, like helium soap bubbles, for example. It is also seen that due to the difference in density between the fluid and the tracer particles, the diameter of the particles should be very small to ensure good tracking. On the other hand, the particle diameter should not be too small, as scattered light, as we will see later, becomes very small also. Finally, in confined facilities such as wind tunnels and other things, or combustion chambers, we use solid particles. This is silica or titanium dioxide. DHS is a class of droplets which shows a response time of about 2 microseconds. And for solid particles, the relaxation time is between 0.4 to 3.7 microseconds. So these are the different time scales that we are operating with. DHS is very good because it has got a very long evaporation time. So these are some of the players. So DHS, silicon dioxide, these are a lot of tracers, or seeders. And this is their mean, response time scale that you can see over here. They are all generated, I think, through certain fluidized bed dispensers or, other types of ways. We will see some of them over there. Okay, and so these are the different, hydrated versus dehydrated and stuff like that. So you can see that, in this particular case, it is a comparison between PIV measurements, which is circles, and the theoretical prediction, which is the black line of particle velocity of titanium dioxide tracers of 0.5 micron along a stationary oblique shock. This is the gas actual velocity because it's very sharp. And this is the velocity that is actually measured, and the other velocity is theoretically predicted. So you can see that there is a time, there is a certain time that it takes, or a certain distance it takes. Okay, so this is the result. Okay, between the PIV measurements and theoretical predictions. Okay, the result for a change in shock velocities, the normal component of the shock velocities. And these are the different response times that you can see over there. Okay, so when you have a neutrally buoyant particle, that is what, in the density of the tracers approaches the density of the liquid they are immersed in. You can see the response time is basically given as delta rho. In this case, delta rho can be made several orders of magnitude smaller than the particle density. In air flows, for example, the density difference between 0.1 kg per meter cube can be easily obtained with helium soaped bubbles, as we said already, compared to 10 to the power of 3 kg per meter cube typical of oil droplets. This condition allows to relax the constraint on particle size, which can be now chosen orders of magnitude larger with little detriment to their time response and tracing fidelity. The measurement of tracers, deceleration, and the velocity slip now allows us to estimate the timely response of these tracers. This is the time response. The particles of approximately 0.3 mm responds to velocity fluctuations within a time scale of 10 to 50 microseconds, because you have reduced the density to almost zero. Okay, this is depending on how close they are to the neutral buoyancy situation. So this is great because you can deal with 0.3 mm particles, which is quite large compared to micron sized particles. So even when the particle slip can be neglected for the purpose of velocity measurements, there are particle drifts that can happen, which can lead to undesired inhomogeneity of the tracers. Remember, we want a homogeneous medium distribution, right? So in this case, for example, this happens when there are vortices and strong vortices and laminar boundary layers. Because of the presence of strong shear and vorticity, the particles tend to accumulate in those areas. Okay. So this is, for example, you can see separation bubble without any particles. Okay. This is separation bubbles with particles. Okay, and this is separation bubbles without particles. So you can see that you may not sometimes have the particles in the flow, and this is clearly inhomogeneous distribution because you can almost see the structures. This is the time averaged particle distribution in the vortices. Just because the particles are entrained in the vortices and they tend to stay there, as a result of that, this leads to inhomogeneity of the tracers, the spatial distribution of the tracers. And once we lose the spatial distribution of the tracers, your velocity measurement is going to suffer big time. At the same time, now let us look at the polar distribution of the light scattered for oil particles of different diameters in air with a wavelength of irradiation of 532 nanometer, most common Nd:YAG lasers. The scattered light is a function of particle size, shape, orientation, relative refractive index, etc. So the contrast, as we know, of the PIV recordings is directly proportional to the scattered light power. So the scattered light power, as we can see, if the particle is 1, the scattering cross section is 10 to the power of minus 12. If the particle size is 0.5, it goes to 10 to the power of minus 12. This is going to 0.1, 0.2, 10 to the power of minus 13, 0.125, 10 to the power of minus 14. So smaller the particle diameter, though it might closely follow the flow, you get a 2 orders decrease in the scattering cross section. So this is, for example, a 1 micron oil particle in air, and this is a 10 micron oil particle in air. And these are in the logarithmic scale, as you can see. As we have illustrated, this is light from this end to that end. As we know, forward scattering is always high intensity, and these lobes are due to the interference between the different scattering orders or scattering modes. And so you can see that there is a lot of difference. Okay, it's a function of therefore the particle size, of course the shape, orientation, and where you are measuring it. Forward scattering, back scattering is always inferior, but you are going to measure somewhere at the, I would say, at the right angle. So this is what you are most concerned with. You are not going to do it there because your imaging in case of PIV is at right angles to the light orientation. Okay, so you have to take into account this because the scattering cross section drops by 2 orders for a size drop of about 1 to about 0.1. So 1 order drop in particle diameter leads to 2 order drops in the scattering cross section. Now, if you are dealing with polydispersed particles, this is like even a little bit of a more complexity because these are Laskin nozzle, you will see what that is. This is DHS particle distribution, okay, and these are distribution based on length, then on area and volume, so they are very different. So the particles with small diameters can be only used if the optical sensitivity is such that it is able to record the images of these small particles. Scattering performance, as we saw, drops quite a bit. Secondly, larger particles actually dominate the PIV signal because it scatters more. So in turn, the measurement fidelity. So the reduction of larger particles is therefore also important, especially when cases when velocity lag needs to be reduced. And thirdly, the quantification of the measurement error due to the velocity lag of polydispersed particles is not easy because you cannot base the calculations with the most frequent size, but it requires more complex procedures. You may have to do in situ measurements with the particles, and need to know the size distribution of the particles and so on and so forth. Okay. So these are the seeding materials for the gas flow. Just remember that polystyrene, alumina, glass microspheres, all of these are candidates. We personally have used all of them. You can also use liquids in the gas flow. This is DHS, which is a diethyl hexyl sebacate. And this is also used. This is about 0.5 to 1.5 micron in diameter. These are all within 3 microns, so to say. Glass beads are microballoons, are typically larger because they have the same density as that of air. So that's why you can go larger by the same principle that we said. From a practical point of view, particles slightly lighter than the liquid will tend to accumulate on the outer edge of the facility sometimes. That can also happen. And this is an example of droplet seeding. This is for the most of the PIV measurement. The Laskin nozzles is used. We have already discussed a little bit of the Laskin nozzles. This offered the advantage of being less harmful than solid particles because it stays in the air but doesn't change in size because of the larger evaporation time. It takes a long time to evaporate. So vegetable oils and DHs are something like that. So that is what we use. We pressurize and then these particles comes out. These droplets comes out as a fine mist. This is the Laskin nozzles, which we already covered a little bit in the PTP and the LTV lectures. And this is a fluidized bed. For example, if you want to generate solid particles, this is powder-based seeding. So you pass the air through a fluidized bed and what comes out of it is basically the particles. In these cases, metal oxide powders are routinely used because of their inertness, high melting point, and low cost. This is particularly important when you are actually dealing with combusting gases because reacting flows you cannot use oil in those cases. Okay, so we will stop here. In the next class, we will take on the lasers and then continue with our PIV.